The question says define acceleration. Well, acceleration is the rate of change of velocity with time. Rate of change of velocity with time. Right, the rate of change of velocity with time, that's acceleration. The next part, a steel ball of diameter that is released from rest and falls vertically in air as illustrated in Fig 2.1. Right. A horizontal beam of light of negligible width is a vertical distance of 0.28 meters below the bottom of the ball. When it is released, the ball falls through and breaks the beam of light. Explain why the force due to air resistance acting on the ball may be neglected when calculating the time taken for the ball to reach the beam of light. Well, the ball has a very small diameter, so the air resistance acting on the ball is quite negligible, because air resistance depends on the dimensions of the object falling through the air. So since this diameter is very small, the resistive forces due to air are very, very small compared to the weight of the object. So we can summarize all this by saying weight of the object is very, very large as compared to air resistance. Right, that's what we can do there. The weight is very, very large as compared to the air resistance of the ball. Right, we are on to item 2. Calculate the time taken for the ball to fall from rest to position P, where the bottom of the ball touches the beam of light. Right, so we have that diagram once again. Let's take a look at it once again. So we want to calculate the time taken for the ball to fall from there, right, to fall from there to there. That we are going to be making use of equations of motion there. What are we given? We are given the displacement. This is the displacement S. What else do we know? We know that G is equal to 9.81 meters per second squared. What else do we know? We know that at this point here, before the ball is released, U is equal to 0. Right, so we have got those quantities. U equals 0, G is 9.81, and S is 0.28. And we want to calculate time. Right, how do we calculate the time? We just find the appropriate equation of motion to use. Right, so the appropriate equation of motion to use in this case would be, S is equal to UT plus half AT squared. Right, now UT, U is 0, so UT there will give us 0. So we'll be left with S is equal to half AT squared. And we know what S is. We want to find T. So T equals the square root of 2S over A. In this case, A is G. Right there. Right, so that will give us the square root of 2 times 2 times 0.28, 0.28, right, all over 9.81, right, and that will simplify to give us 0.23892. Right, we have to leave our answer to a reasonable number of significant figures. So in the data that we've been given 0.280. So this figure is to 3 significant figures. So we should leave our answer to 3 significant figures, because that was 3SF. Let's leave our answer to 3SF. So we will have our answer as 0.239 seconds. That's our answer right there. Right, we are on to item 3. Determine the time interval during which the beam of light is broken by the ball. Right, okay, so here what we're going to do is we are going to find the time taken by the ball. Find the time taken by the ball to move through a distance of 0.28, 0.28, 0.28 plus the diameter of the ball right there, which is 0.08 meters. Right, that's the time interval. That's what happens when the beam of light is broken. The ball first falls through 0.28 meters, then it falls through an additional 0.08 meters, which is the diameter of the ball. So what is the time from when the ball is released? What is the time that the ball will take to travel through a distance of 0.36 meters? Let's find that time. Right, so time taken to travel through 0.36 meters. Again, we make use of the equation of motion, which says S equals ut plus half at squared. In this case, our a is g and our u is 0, so S is equal to half gt squared. Right, we want t, so t equals the square root of 2s over g. That in this case our s is 0.36 meters, so we make sure that we substitute s with 0.36 meters right there. Right, if we input this into our calculator, we get 0.271 seconds. Right, so we keep this result, 0.271 seconds, and we have to calculate the time interval from that the beam of light is broken. So remember time interval, remember time interval, time interval from release up to when beam is cleared, when beam is cleared, that is equal to 0.271 seconds. Right. And we have time interval from release to reaching the beam. Time interval from release up to when the ball reaches the beam, it's 0.032 seconds. So 0.032 seconds is our time interval right there. 0.032 seconds is the required time interval there. A different ball is released from the same position as the steel ball in B. This ball has the same diameter but a much lower density. For this ball, the force due to air resistance cannot be neglected as the ball falls. State and explain the change, if any, to the time interval during which the beam of light is broken by the ball. Right, so we have two factors at play. Firstly, the density is lower, which means the weight of this ball is lower. Secondly, the air resistance is greater. So the time interval for which the beam of light is broken increases because air resistance decreases the acceleration of the ball.